Welcome to the second Horvick Research Science Gem. This second video will take a closer look at the way the brain creates for you your own inner brain matrix and how chiropractic can influence your perception of reality. If you have seen the movie The Matrix, you'll remember Thomas Anderson, who was a computer programmer, but who also maintained a double life as a hacker, Neo. He was intrigued by the cryptic references to the Matrix that appeared on his computer, and he meets up with the infamous hacker Trinity, who informs him that a man named Morpheus can tell him more about what the Matrix actually is. Eventually, Neo meets up with Morpheus and confirms that he wants to learn more about the Matrix by choosing the offered red pill. After swallowing the pill, Neo abruptly awakens in a fluid-filled vessel. His body is pierced with cables that connect him, along with billions of other people, to an elaborate electrical network. Morpheus tells Neo that the humans are fighting against intelligent machines that were created in the 21st century and have since taken over Earth. The machines are using human bioelectricity as a power source, so Neo has been living in a simulated world since he was born. So basically, Neo's life was an entire lie, created by intelligent machines by plugging into his central nervous system. So how does this relate to us and to chiropractic? Well, our brains basically create for us a virtual reality, or a matrix, via our 5 senses: your ears, eyes, nose, taste, and touch. In fact, we have more senses than that, and our brain uses all of them as well. We have senses that detect temperature, proprioception, kinesthesia, pain, balance, and various chemical reactions. In addition to all of these types of sensory inputs, your brain will also take into account your past experiences and your expectations for the future. And based on all of this information, your brain will create for you an inner reality about what is actually going on in and around your body. You are not usually consciously aware of all of this processing. You only experience your own reality. Basically, your brain is taking care of a lot of background processing without you being aware of it. The interesting thing is that what your brain is telling you as your reality may not be 100% accurate. It may not reflect what is actually going on. A good example of this is the classic checker shadow illusion created by Edward Andelson from the Massachusetts Institute of Technology. Take a look at square A and square B. Square A looks darker than square B. However, if I cover everything up except those 2 squares, you can see for yourself that they are in fact identical in color. This is quite incredible, isn't it? Because your brain doesn't just see what the eyes tell it, it interprets what the eyes tell it based on all kinds of other information and expectations. The brain will take into account where you are, what you're doing, what your intentions are. It will compute shadows and light sources. And only after all of these computations, that by the way only take a few milliseconds for your brain, it will then actually see what you see, or tell you what you see. In this case, the square A looks darker than square B because square B is in the shadow cast by the green cylinder, while square A is outside of that shadow. So based on your brain's past experience, it will decide for you that if a square in a shadow reflects the same amount of light as a square outside of the shadow, then it must be a lighter shade of grey. So your brain actually alters your perception of the image. It changes your inner reality so that you see what it thinks is out there in the real world, not what actually is out there. Now we're going to take a closer look at the connection between neuroscience and chiropractic. We're going to look at exactly how chiropractic is likely to be affecting these various neurophysiological processes in the brain, and later we'll look at some of the research that has demonstrated this link. So bringing it all back to chiropractic, one key component in the proposed theory about the neurophysiological mechanisms of chiropractic care is the functional role of paraspinal muscles. We know, for example, that the muscles in general provide the brain with feedback about what muscle is doing. But we also know that the small paraspinal muscles, particularly in the upper cervical region, they're chock full of sensory organs. So scientists are now arguing that for this reason, because they're chock full of sensory organs, and for biomechanical reasons, that these small paraspinal muscles' primary function is sensory and not motor. The sensory organs I'm talking about are of course muscle spindles. It's really important to understand how muscle spindles work to understand the functional role of these deep paraspinal muscles. Muscle spindles detect stretch. So from all of your muscles all over your body, your brain is receiving messages from muscle spindles about what's happening in that muscle. And if you record from them, which we have actually done, you can actually hear them. So if you've got a normal muscle, it's going tick, 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 tick to the brain. And then if you stretch the muscle, it goes tick, 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 tick. And then you slacken the muscle off and it goes tick, 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 tick. And so in this way, your brain is receiving all this information from muscle spindles all over your body all the time. If the muscles are not getting stretched, there will be much less information going to the brain where those muscles are. So muscle spindles play a very important role in sensory-motor integration, and most likely play a key role in the mechanisms of chiropractic care. Because their basic role is to sense stretch of muscles, and by doing so, they are continuously informing the brain about the length and the change of length of all your muscles in your body. And we know that the number and density of muscle spindles are remarkably high in the upper cervical and suboccipital deep paraspinal muscles. We also know that these muscles are very small and seem incapable of bringing about any significant head movement compared with the bigger muscles and the more powerful muscles that also have better mechanical advantage to bring about movement. So current thinking is that the functional role of these small deep paraspinal muscles are proprioceptive sensors and probably play less of a significant role in movement. And we know from the chiropractic literature about the function of these muscles that they play a significant role in the neurophysiological mechanisms of chiropractic care. So there is evidence in the literature that spinal sensory information is important for the brain to integrate other sensory information. In this particular paper, the authors were investigating the influence of neck pain on sensory motor function in older adults. They concluded that their elderly subjects with neck pain had altered afferent information originating from their cervical spines, and that they believed this caused greater sensory motor dysfunction compared to older adults that did not have neck pain. The authors basically argued that it would influence the ability of these older adults to maintain balance and prevent falls. So in this study, they ran a whole lot of sensory motor functional tests and took into account actual age and other comorbidities. These authors were pretty much saying that the altered afferent input from the cervical spines of these older adults that had neck pain was disturbing their brain's ability to integrate and process all other sensory information required to have good balance and prevent falls. Other studies from back in the mid-90s, when Professor Walter Herzog and his colleagues at the University of Calgary demonstrated beautifully over a series of experiments that spinal manipulation thrusts can evoke short-lasting electromyography or EMG reflexive responses from paraspinal skeletal muscles. The EMG responses could even be recorded from more distal muscles further away from the segment that was adjusted, and they have shown this with both thoracic adjustments and cervical adjustments. What's really interesting was that the speed of the thrust was what mattered the most to elicit the neuromuscular response. Therefore, it appears that the production of these reflex responses depends directly on the rate of change in force during an adjustment rather than the actual force itself or the overall degree of stretch. Paraspinal muscle spindles are the most likely candidates to be the contributors to these EMG responses that Walter Herzog and his colleagues recorded. And if you think about it, our chiropractic adjustments are very likely to have a direct effect on muscle spindle activity in paraspinal muscles because they're likely to stretch the little muscles that attach to the vertebra above and below the segment that we adjust. Joel Pekar and his colleagues at the Palmer Center for Chiropractic Research in Davenport, Iowa, have also shown in anesthetized cats that muscle spindles in the paraspinal muscles do respond to vertebral loads that have the same force time profiles that occur when we deliver an adjustment. These force time profiles have been documented extensively in many studies. So Joel and his colleagues basically recorded directly from axons of nerve fibers that had either originated from Golgi tendon organs or muscle spindles in the paraspinal muscles. This was all recorded in anesthetized cats. They found that muscle spindles tended to increase their firing rate by almost 30%, even just during the preload application when you're getting set up for an adjustment. And then they responded with an increased firing rate of about 200% more with the actual thrust. Then the spindles would be silenced for about 1.3 seconds on average before they resumed their background resting firing rate. So when we have a segment in the spine that is not moving properly, for example if it's stuck, what some of us call subluxations, this is going to reduce the amount of stretch of the deep paraspinal muscles that attach around that stuck segment. So this means that the muscle spindles will be firing less, so the brain will be getting less information from that segment. This can be a little bit like an electric circuit breaker blowing. Let me explain this with an analogy. Imagine you've lived in a house all your life. And imagine there was a circuit breaker in that house that blew, that caused all the lights in a very long dark corridor in your house to go out. And there's no windows in this corridor. So you are pitched into complete darkness. Now could you walk down that corridor to the end and flick back the circuit connection? Of course you could. You've lived there all your life. You know roughly how long the corridor is, you know roughly how wide it is, you know roughly where the circuit box is, even if it's totally pitch black. In just the same way, if we had a stuck segment in our spines, our brains may be in the dark about what's happening in our spine, and this lack of information may influence how your brain processes other sensory information. But your brain has been controlling your body all your life, and even if it doesn't get some information about your spine, it can make a very good educated guess about what's going on based on your past experiences. So most of the time this might be fine. But let's go back to that dark corridor analogy again, and imagine that your kids had left a toys or a bike in that corridor that you hadn't seen before the lights went out. In that scenario, you would most likely trip over the toys and have an accident. And in just the same way, if you've got stuck spinal segments in your spine and the paraspinal muscles surrounding that segment are not being stretched and therefore not firing their information to the brain, your brain is in the dark about what's going on in that part of your spine. It can guess what to do, but it might not guess correctly. So this could lead to maladaptive neuroplasticity, accidents, and the development of disorders. This picture sums up the model that I'm talking about. So put very simply, we're arguing that if you've got a segment in the spine that's not moving properly, what we call a subluxation, this will be sending different afferent information from the paraspinal tissues surrounding the segment to the central nervous system. And we know that if you alter the afferent input into the central nervous system, it will change the way the brain processes and integrates all other incoming information. This is logical based on what we know about neuroplasticity. We have also hypothesized that through the chiropractic adjustment, we restore appropriate segmental movement, which leads to a more appropriate segmental afferent input, which will in turn allow the brain to process and integrate information in a more accurate manner. According to this, the subluxation can be viewed as a self-perpetuating central segmental motor control problem that leads to ongoing maladaptive central plastic changes. Now this is a key concept, so I'm going to repeat it. According to this, the subluxation can be viewed as a self-perpetuating central segmental motor control problem that leads to ongoing maladaptive central plastic changes. Let's take a closer look. If a spinal segment is not moving appropriately, there will be altered afferent information going to the brain. The paraspinal muscles are not going to be stretched in the same way if there's a change in movement patterns. And if you change afferent information to the brain, we know that this leads to neuroplastic changes. There may be alterations in the way the brain filters information, the way it processes proprioceptive information from the body. It can alter sensory-motor integration and therefore affect motor control. And for some people, this can lead to pain and dysfunction. When we adjust the spine, we normalize that afferent information from the segment, improving proprioceptive filtering and processing, improving sensory-motor integration and motor control, and thus leading to more healthy function. So is there any evidence for this theory? Well, the cool thing is, yes, there is. There is a growing body of scientific evidence that is congruent with this model. As opposed to other ways of explaining how chiropractic works, like a bone out of place, pressure on a nerve, or a foot on the hose pipe type of explanations, what I'm talking about in this video is actually congruent with the current scientific literature and understanding. And there is animal research studies that have shown that if you malposition a vertebra, it is signaled to the central nervous system via deep muscle afferents, and interestingly not via joint afferents. And we know from a variety of studies that prior to being adjusted, the central nervous system processes, integrates and filters proprioceptive afferent information in a different way compared to after being adjusted. And there's a growing body of research evidence showing a variety of improvements in central nervous system function after spinal adjustments. And it's an important fact to consider that the majority of these studies that my group has conducted has been in subclinical pain populations. So this means people who are developing pain and problems, so they had reoccurring intermittent neck pain, ache or stiffness, but had not yet sought treatment for their problems. And most importantly, they were symptom-free on the date of data recording. We have very carefully chosen this population to study because we wanted to know what happened when we adjusted subluxations in people without the confounding presence of pain. If our subject had been in pain, and pain changed as a result of our chiropractic adjustments, then we would have no way of knowing whether the changes that were taking place within the central nervous system were just simply due to a change in pain. We do know, based on the studies that have been done in the subclinical pain group, because they did not have pain on the day we studied them, that the changes are likely due to adjusting subluxations, or the chiropractic care that was delivered that day. This model is the foundation of our understanding of how chiropractic works. In the next Science Gems, I'm going to start to take a look at how to talk about individual studies, and we will start by looking at 2 key scientific studies that are real gems. I hope by now it's starting to become clear why I say that chiropractic is a healing art that improves the health and function of the spine, which in turn helps clear up the communication between your brain, your body and the environment, so it can accurately perceive what is going on and therefore respond appropriately. This is what the literature is telling me, and I will over the next few videos come back to this in greater detail. In wrapping up, I'd like to take this opportunity to invite you to join us at the forefront of chiropractic research by joining the Centre for Chiropractic Research Supporters Program. If you would like to invest in our collective future and support the research work we are doing, please join the Supporters Program. 100% of all donations go directly to the Centre for Chiropractic Research, where we are working as hard as we can on our quest to understand how chiropractic works. I really hope you found this video useful, and I look forward to hearing from you with feedback about how we can make these videos even better for you.